Namaste, everyone, and welcome. Have you ever looked at a really long, complicated digital logic equation and just thought, Yard, there has to be a better way to do this? Well, guess what? You're in luck. Today, we're going on a little quest to find a super simple visual trick to solve these exact kinds of puzzles.
So here's the game plan for today. First, we're going to talk about the Boolean headache. Why we need a shortcut in the first place. Then, we'll meet our hero, the K-map, and learn the rules of the game. After that, we'll unlock a pretty cool power-up with Don't Cares, figure out where the K-map's limits are, and finally, get to the main point, your big simplification takeaway. Cello, let's jump right in.
All right, first things first, let's talk about the Boolean headache. Look, if you've ever dealt with a circuit diagram or a truth table, you know the number one goal is always to make it simpler, right? But trying to do that with just pure algebra? Oh boy, that's where the headache really begins.
I mean, just imagine trying to simplify a long Boolean expression like this one. It's a mess of variables and logic gates. Honestly, using only the algebraic rules is like trying to untangle your headphones in total darkness. You make one wrong move, and the whole thing just gets worse. It's slow, it's tedious, and it's basically a perfect recipe for making a silly mistake.
But what if I told you there's a visual way to do this, like a cheat code for digital logic that lets you see the answer just by spotting some patterns? Sounds a lot better, doesn't it?
And that, my friends, brings us to our hero for today, the Karnaugh Map, or as everyone calls it, the K-map. This is the amazing tool that's about to make all our lives so much easier.
So what exactly is this K-map? Well, the easiest way to think about it is like a truth table that's been cleverly rearranged into a grid. You just pop in your ones and zeros, and the real magic is in how it's all laid out. The arrangement literally makes the simplification patterns jump right out at you. So you can forget memorizing complex theorems. This is all about just spotting patterns.
And just look at this comparison, it says it all. On one side, you've got Boolean algebra, it's all text, you got to remember a ton of different laws, and it's so easy to make a mistake. But then you have the K-map. It's visual, it's intuitive, and for anything between, say, 3 to 6 variables, it is way faster and much less error-prone. It's a total no-brainer, really.
Okay, so now that we've met our hero, it's time to learn its moves. To really unleash the power of the K-map, we just need to understand a few simple rules of the game. It's easy, I promise. So here's the basic 4-step plan. Step 1. Pick the right size map depending on how many variables you have. Step 2. Fill in the map with your ones, based on your logic function. Step 3, and this is the most important part, you circle the largest possible groups of ones you can find. And finally, step 4, you just write down the simplified expression you get from those groups. That's it. Simple as that.
Now, you might be wondering, what's the secret sauce that makes this all work? Well, it's something called gray code. You see, in a normal binary count, lots of bits can flip at once, right? But in gray code, only one single bit changes between any two cells that are next to each other. So why does that matter? Well, in Boolean algebra, terms that differ by only one variable are the ones you can simplify together. Gray code is a brilliant hack that puts these terms right next to each other on the grid, making them super easy for our eyes to spot and group. It's genius, really. And when you're making those groups, just keep these simple rules in mind. First, all your groups have to be either rectangles or squares. Second, the size of your group has to be a power of 2, so a group of 1, 2, 4, 8, and so on. Also, it's totally fine to let your groups overlap if it helps you make an even bigger group. But the one big no-no is grouping diagonally. Don't do that. That's against the rules.
Now this brings me to one of the coolest features of the K-map, the wraparound. The best way to picture this is to imagine the map is printed on a piece of paper. Now roll that paper up into a cylinder. See how the left and right edges are now touching? Well, it's the same idea here. The same goes for the top and bottom edges. This means you can actually group ones on completely opposite ends of the map together, which is a really powerful trick.
Okay, so once you get the hang of the basics, it's time to unlock a special power-up. This is a bit of a pro-level trick that makes K-maps even more powerful. We call it the don't care condition.
So, what is a don't care condition? You'll see it marked with an X on the map. It basically means that this particular input combination will just never happen in your circuit. And here's the best part. You get to decide if you want to treat that X as a 1 or as a 0. You use it as a 1 only if it helps you make a bigger group. It's basically like having a wild card in a game of cards.
And why is that so useful? Well, think about it.
Bigger groups give you a much simpler final expression, and a simpler expression means you need fewer logic gates to actually build your circuit. And of course, fewer gates mean your circuit is cheaper to make and more efficient to run. So yeah, using don't cares is just plain smart engineering. Now, our hero, the K-map, is absolutely amazing, but it's not invincible. Like any hero, it has its limits, and it's really important to know when to call for some backup.
You see, the thing is, K-maps are a manual tool, right? We humans have to draw and read them. And they work beautifully for problems with up to about 6 variables. But as soon as you go beyond that, the map just gets huge. It becomes way too big and visually complicated for us to handle on paper. It gets very, very messy, very fast.
This little table here is a great rule of thumb to follow. For really simple problems like 2 or 3 variables, honestly, either method is fine. But the K-map really hits its sweet spot between 4 and 6 variables. That's where it's just so much faster and safer than algebra. But once you get past 6 variables, yeah, the map becomes a bit of a monster, and it's time to let the computers take over.
For those really, really complex problems with tons of variables, we switch to powerful computer algorithms. A famous one you might hear about is the Quine-McCluskey method. So you can think of the K-map as the perfect stepping stone. It's what you learn that helps you understand how these more advanced, automated tools actually work.
And with that, we've reached the end of our little quest. We've seen the problem, we've met our hero, and we've learned its powers. So now, let's talk about the treasure. What is the big takeaway from all of this? Why does it matter? Okay, here are the key things I really want you to remember. First, K-maps transform a difficult algebra problem into a simple visual puzzle. Second, they're faster and way less prone to errors than just using Boolean laws. Third, they directly help you build digital circuits that are more efficient and cheaper. And finally, don't forget your secret weapon. Those don't care conditions are the key to getting the absolute best simplification.
So there you have it. The Karnaugh map really is like having a superpower for simplifying digital logic. The only question left is, now that you have this power, what complex problem are you going to simplify next? Happy simplifying!